Hi students, I am Sindhu N. Iyer, PGT Chemistry from KVNAD Karanja. We have discussed surface chemistry, we have discussed chemical kinetics, etc. in previous classes. Today I am going to give you a lecture on coordination chemistry. It is a very interesting topic for you. As the name indicates what the coordination chemistry means, what does how the compound complexes are formed, what are the theories behind it, all things we will discuss in this chapter. The first session what I am going to discuss with you is coordination complexes, coordination entity, ligands, denticity, coordination number, coordination polyhedron, homoleptic and heteroleptic complexes. In the sense, first what are coordination compounds, that I need to tell you first. Coordination compounds are those in which are formed by transition metals, especially in which the central metal ion and ligands are involved. Ligands in the sense, for example, if I take cobalt, it combines with ammonia molecule, 6 ammonia molecule, and form a coordination complex where there is the species which are combined with the central metal ion are known as ligands, and this metal ion which is present within the square bracket. A coordination compound always has got 2 parts. One is a square bracket which we call it as coordination polyhedra, and the ions which are present outside the square bracket which are called as counter ions. If I write K4 FeCN6, as I told you, this is the square bracket or coordination polyhedra, and potassium is a counter ion. This case coordination polyhedra is this, and chloride is a counter ion. Like that, a coordination compound, we are only concerned with the part coordination polyhedra or the metal as well as the ligands which are attached with the central metal ion. So, students, is it clear to you? I hope what are coordination compounds, where the central metal ion reacts with the ligands or combine with the ligands through coordinate bond. Coordinate bond means the bond, electron pairs are donated by only one species. It is a type of covalent bond only. After the bond formation, it is a covalent bond only, of course, but the electron pairs which are present in ammonia, lone pair of electrons which are present on nitrogen will be coordinated with the empty orbital of cobalt. Here the electron pairs which are present on cyanide group will be coordinated to the empty orbital of iron. So, this bond formed between the metal and ligand is coordinate in nature. So, we call the compounds are coordination compounds. Now, as I told you, there is a central metal atom. The metal which is attached with the ligands through coordinate bond, and the metal of course will have an oxidation state. Either it is 0 or it will have an oxidation state. How to calculate the oxidation state of the metal ion? We follow the same rules as what we studied in class 11th. You studied how to calculate the oxidation state of an element. For example, if I take the first case, it is very easy to understand. This ammonia, water, etc. Ammonia, water, etc. are neutral ligands. Ammonia, water, etc. are neutral ligands. OH minus, Cl minus, F minus, these are negative ligands, ligands which are having negative charge. So, ligands can be either negative or it can be neutral, which are capable of donating a pair of electrons. Why these are capable of donating a pair of electrons? Because nitrogen contains a lone pair, oxygen contains a lone pair. So, in ammonia, nitrogen contains a lone pair which can be donated to the empty orbital of the metal. In water, it contains, who contains the lone pair? Oxygen contains the lone pair which can be donated to the empty orbital of the metal. So, in that case, this will be acting as ligands. So, you should know the charge of various ligands that I will be giving you in continuation with us. When we come to the nomenclature, I will discuss it in detail. But you should know, if there is no charge given on the complex, this case as a whole the complex is neutral. To find out the charge of central metal ion, what we have studied in class 11, the same procedure has to be followed. How? This is a counter ion, you do not bother about it, only we have to bother what is the charge of this counter ion. Since it is chloride, you know that its charge is -1. 3 chloride, so it will be minus 3. So the polyhedra will have a charge of plus 3. What is this plus 3? This plus 3 is the total charge of all the atoms and ions which are present inside the, all the molecules and ions which are present within the polyhedra. So this will be 6, so it is ammonia is a neutral ligand, as you know. 6 ammonia plus 1 cobalt. Cobalt will have of course a charge of plus 3. That is why plus 3 plus 0, it has got a charge of plus 3. This case, so what is the charge of central metal ion? The central metal ion has got a, the central metal ion has got a charge of, what is the charge of central metal ion? The central metal ion has got a charge of plus 3. This case you see, potassium, of course you know the central metal ion, the potassium has got a charge of plus 1. There are 4 potassium ions, so the charge will be plus 4. So the coordination entity, coordination polyhedra will have a charge of minus 4. Of course, cyanide, one cyanide has got a charge of minus 1. So there are 6 cyanide, so it will be 6 minus. Total charge of the square bracket is minus 4. So what will be the charge of iron? It will be plus 2. Hope you understood what I told. From this, 2 things are clear to you. The counter ion, the ions which are present outside the square bracket, which are called counter ions can be negative, can be positive. This case it is negative, this case it is positive. If the counter ion is negative, square bracket will have a positive charge. If the counter ion is positive, square bracket will have a negative charge. So the polyhedra can be negative, total charge of the polyhedra can be negative or it can be positive. Hope you understood what I told you. When we need to do the nomenclature, that time these terms are very important. Next thing is ligand, I have explained to you. Ligands are species which are having either negative charge or they are neutral species which are capable of donating minimum 1 pair of electrons to the central metal ion, or they are capable of coordinating with 1 pair of electrons. For example, water, ammonia, these 2 are neutral ligands. These are negative ligands. There are ligands which are capable, so these ligands are called unidentate ligands which are capable of donating only 1 pair of electrons, 2 electrons to the central metal ion. These all are unidentate ligands. This can donate only 1 pair of electrons, this can donate 1 pair of electron, this can also donate 1 pair of electrons. Since there are only 1 lone pair on nitrogen, it can donate only 1 pair of electrons. In water, though there are 2 lone pairs, at a time it can coordinate with only 1 lone pair. So it is also a unidentate ligand. There are bidentate ligand, for example, ethylene diamine, CH2NH2, CH2NH2, this is ethylene diamine. So this compound, it can coordinate with the central metal ion with the 2 lone pairs. So it is called a bidentate ligand. Means what is meant by denticity? How many electron pairs at a time a ligand can donate to the central metal ion. How many electron pairs at a time a ligand can donate to the central metal ion, or with how many electron pairs a ligand can combine, form coordinate bond at a time. How many electron pairs at a time the ligand can donate to the central metal ion? In this case 2. So it can donate 2 electron pairs at a time to the central metal ion. So this is called bidentate ligand. Oxalate ion, COO minus, COO minus. This can also donate 2 electron pairs at a time. So it is also a bidentate ligand. There are ligands, for example, EDTA, ethylene diamine tetraacetic acid 4 minus ion. It can donate 4 electron pairs at a time. So it comes under the category polydentate ligand. Ligands which are capable of donating more than 2 pairs of electrons at a time are called polydentate ligands. Hope it is clear to you. What is denticity? The capacity of a ligand to donate electron pairs to the central metal ion is called denticity. These ligands can donate, polydentate ligand can donate more than 2 pairs of electrons to the central metal ion at a time. Bidentate can donate only 2 pairs of electrons or 2 coordinate bond it can form at a time. Unidentate can form only one coordinate bond, or it can donate only one pair of electrons to the central metal ion at a time. Hope it is clear to you. Now, you can see if a polydentate or a bidentate ligand which is combining with the central metal ion, for example, if I write COEN twice, means ethylene diamine, two ethylene diamine molecules are, I am writing thrice. Thrice, if I write, this case, it forms a ring with the central metal ion. It forms a ring with the central metal ion. So, we call it as a chelating ligand. The ligand which forms more than one coordinate bond and it forms a ring with the central metal ion, we call the ligand as chelating ligand. In denticity, one more term which comes, which is ambidentate. For example, NO2 ion, this species, we can donate electron pairs from nitrogen as well as oxygen. So, we can write it as NO2. If nitrogen is donating electron, we write it like this. If oxygen is donating electrons, we write it like this, ONO. You are familiar with NO2. It can donate electron pairs either through nitrogen or through oxygen. If nitrogen is donating electron pairs, we write it as NO2. If oxygen is donating electron pairs, we write it as ONO. O-nitrito and N-nitrito we call it. Means, but at a time either nitrogen will donate or oxygen will donate, both at a time is not possible. Same way, thiocyanate, SCN, NSC, these ligands, you can see the specificity, we cannot say they are bidentate, they are unidentate only. At a time, only one pair can be donated, either from nitrogen or from sulfur, or either, first case, either from nitrogen or from oxygen. Such ligands which has two options, either from here or from here. Ligands which are capable of donating one pair of electrons, two pair of electrons, but one pair at a time. Such ligands are known as ambidentate ligands. These ligands are known as ambidentate ligands. I hope the term ambidentate, polydentate, bidentate, unidentate all clear to you. Now, it comes to the coordination number. In coordination number, that is very simple. If I write CONH3 6 times, now it comes to the term coordination number. Coordination number means with how many ligands the central metal ion is being coordinated. In a polyhedra, for example, CONH3 6 times 3 plus, NiCO4 times, these all cases, how many ligands are coordinated with the central metal? How many ligands are, or how many coordinate bond it has formed? Here, how many coordinate bond it has formed? 6. So, the coordination number is 6. Here, how many coordinate bond it has formed? 4. So, the coordination number is 4. Coordination polyhedra. Now, we are going to discuss coordination polyhedra. Coordination polyhedra, you need to understand the thing which is present inside the bracket, or the geometry of the ligand is, or geometry of the complex is determined by the coordination polyhedra. For example, there are 6 ligands which are attached with the central metal ion. If the coordination number is 6, automatically what we feel the geometry is octahedra. If the coordination number is 6, automatically we feel the geometry is octahedra. If we draw it, children, you see it, cobalt at the center, and ammonia at the corner, this is a structure of an octahedron. See, if the coordination number is 6, it can be an octahedra. If the coordination number is 4, it can be a tetrahedra. For example, nickel with 4 ligands. It's not necessary that it is only octahedra and it is only tetrahedra. It can be, but then the coordination number and the central metal ion decides what is the structure the polyhedra has. That is called coordination polyhedra, the geometry with which that polyhedral structure which arises due to the coordination between the central metal ion and the ligands, which are known as with that geometry is called polyhedra. Now it comes to homoleptic and heteroleptic ligands. Homoleptic in the sense the central metal ion carries only one type of ligand. Heteroleptic means the central metal ion carries more than one type of ligands. You see here, CONH3 6 times 3 plus. This case there is only one type of ligand, so it is a homoleptic complex. This case you see CONH3 4 times Cl2. There are two type of ligands, so it is a heteroleptic complex. Hope you understood what I told. I am going to discuss about the nomenclature of coordination compounds. As I have told you, there are two categories of coordination compounds. First category, the square bracket is positive. Second category, the square bracket is negative. So first we discuss the square bracket is negative or it is neutral. Either the square bracket is negative or the square bracket is neutral. Means coordination entity is negative. Here all the compounds whichever I have written, this potassium, so naturally it is positive. So the coordination polyhedra or coordination entity will be negative. Here it is Na3, so the polyhedra will be minus 3. Here it will be K2, so of course it will be minus 2. This case you see, here the coordination polyhedra is neutral. This case you see, since it is sodium is plus, this will be minus. So the coordination entity is negative. That case first we are going to discuss. You should remember there is an IUPAC system of nomenclature which is given for the ligands as well as the coordination compounds, how to name it. If the ligand is a negative ligand, it should end with O. Remember, the ligand is a negative ligand, it should end with O. If it is chloro, instead of chloro, we call it as chlorido, bromido, and cyano, oxalato, sulfato,